Hello and welcome to a small discussion on a very interesting topic, which is the topic of Laplace Runge-Lenz vector. So, this is a vector which is conserved only in the case of an inverse square force law. This is not a conserved quantity for a general central force motion, but it is a specific conserved vector for inverse square law force. Okay. So, in this lecture I will simply, in this small discussion, I will simply show the conservation of this, and I will put some questions which will be very interesting for you guys to think. So, A is given, this is the Laplace Runge-Lenz vector, which is given by the this expression, which is the cross product of the linear momentum vector and the angular momentum vector minus m k times r cap vector. K is the constant of the force, okay, m is the mass of the particle. Now, why this is conserved in a motion under an inverse square force? So, for that we start just by doing this demonstration. So, ddt of p cross L, I can always write this as dp dt cross L plus p cross dl dt. Remember, when we do ddt of the cross products, the order should not be changed of the vectors. Okay. Now, this one we already know this is equal to 0 for any central force, that we will use, and we will simply have this is equal to dp dt cross L. Okay. And then in the next step we will simply write again. So, what is dp dt? We have to understand this is nothing but the force itself. So, I can easily say this is the force law. So, which is nothing but, I can write here is f of r times r cap. Okay. For the time being, I am simply writing this expression over here. So, this is the force. So, it will be f of r times r cap cross L. Now, L, instead of L I can also write this f of r cap cross r cross mv. So, this is L, this one is L, that I can write. I can write f of r cap cross r cross m dr dt. Okay. And then you can write, of course, this is equal to m f of r. Now, I take an r over here and I make this one as a r vector. Okay. So, then I can simply say that I will have r vector cross r cross dr dt. Okay. If I can do, I can then use for this part, this is a vector triple product, I can use back cab rule, as you all know, m f r by r. Then I can first take r dot dr dt times r minus r square dr vector dt. Okay. Now, the first one you know, whenever I talk about this r dot dr dt, this is a very important conclusion, is equal to also r dot dr dt, because both of them are actually equal to ddt of r square by 2. Now, r square actually comes in two ways, r square is equal to mod r whole square, and it is also r dot r. Okay. So, that exactly we use here to get all these things. Okay. I can then write this is equal to m f of r by r dr dt r vector minus r square dr dt. Okay. I have this thing, and then I can write that, okay, I have m f r, I take this r inside, and I will have dr dt r vector minus r dr vector dt. Okay. I then do something very interesting. I will multiply and divide the whole thing by r square. And then what I will get by this interesting multiplication and division is the following. Then I can take m f r times r square, then this 1 by r square I will include that inside the bracket, and I will simply have this 1 over r square dr dt r vector minus 1 over r dr vector dt. Okay. And I take a global minus sign now common, m f of r times r square, and I write the expression as 1 over r dr vector dt. Okay. I just take a minus sign throughout common, okay, and I will have plus minus of 1 r by r square dr scalar dt r vector. And if you just check this expression carefully, you will see this expression is nothing but d dt of r vector by r. Okay. And so, d dt of p cross L comes to be, so I can just write, so d dt of, d dt of p cross L is equal to minus m f r times r square d dt of r vector by r. Now, what is f r? F r is, if you remember, minus k by r square. So, f r times r square will be minus k. So, there is a minus, so it will be m k d dt of r vector by r. Okay. So, you see d dt of p cross L minus these both are constant. So, I can write m k. What is r vector by r? This is nothing but r unit vector, okay, that will be 0, and you can finally say that is my a vector. So, which is the Laplace Runge-Lenz vector. Okay. Now, Laplace Runge-Lenz vector is conserved. For example, when something is conserved, something is 0, something is conserved, we have some intrinsic meaning. For example, we say that okay, whenever there is no torque, the angular momentum is conserved. Okay. And whenever we say that there is no force, the linear momentum is conserved. So, actually in some later lecture I will also discuss some symmetry and the conservation, some relation between symmetry and conservation, and you will see that always with some this type of conservation principle there is a continuous symmetry associated. And so, my question is, can you also find some other meaning? So, is this just an accident, the conservation of Laplace Runge-Lenz vector, or this is just a mathematical output which does not have any meaning, I mean at least, or can you at least make some geometrical meaning, geometrical significance from that related to the nature of orbits and everything like that, and tell me that what is the meaning of this conservation of this Laplace Runge-Lenz vector. There are two very important points for that. I am giving you a hint. Okay. What you have to do, you have to find three things. One is a dot L. So, what is the, and that means that actually I am interested to know the angle between the angular momentum vector and the Laplace Runge-Lenz vector. Then a dot r or r cap. Okay. So, the radius vector and the Laplace Runge-Lenz vector, and finally modulus of a, okay, or its square. If this is a constant vector, of course, you have to know that this is also a constant, the magnitude is also constant. Now, my point is that using these three elements, can you find some interesting conclusion about the nature of the trajectory or something under an inverse square law and the significance of the conservation of Laplace Runge-Lenz vector. Okay. Thank you very much.